Thank you for the introduction. So again, just a short intro. I'm Thivin. I'm a PhD student at Department of Computational and Data Sciences at Indian Institute of Science, Bangalore. So today I will present my work on GPU accelerated FEM-based Lagrangian particle tracking for human pathways. So again, the motivation is to develop a better and robust GPU-based routines which can perform efficient particle tracking with limited amount of data or the complex data structures required as possible. The idea to bring in FEM is the part that when we worked with FEM, do realize that lot of things that are highly time consuming and the things that takes up most of the bottlenecks, such as like identification of particle position in a computational domain and interpolation of velocities, can be done a little more efficiently on CPUs because of the way the FEM data structures have been rich with mesh related data structures and so on, so interpolation capabilities. However, when I decided to do those on GPU, I did came into really there were a lot of complexities that we have to handle in order to, let's say, replicate those calculations within GPU. So we did simplified a lot of calculations in the data structures that are required to perform these perform this tracking inside GPU. And also we implemented some of the zonal based particle tracking to effectively track particles within the GPU with those limited data. What we show is of a validated sequential implementation with standard libraries. We show 100x speedups in terms of when compared to the sequential version. Okay, so to give you a very basic idea, we performed our simulation on a mesh with the 0.3 million shells. Again, this is, as you know, for a given complex geometry like a human error pathway, this is exactly not feasible or good enough resolution to solve the fluid flow. But again, this was again taken to just implement the methodology on GPU, then later stages to do simulations on a highly refined mesh and so on. So, okay, so these are the incompressible Navier-Stokes equations. The boundary conditions for this are inlet will be a Dirichlet inlet with turbulent characteristics in flow, and your outflow or your wall condition is like no slip, no penetration, and your outflow is a zero Neumann boundary condition. Again, to start with, we did some laminar simulations with our framework to check if our framework is working correctly in terms of the solvers or not. And these are the results, some of the results obtained with the laminar flow. For the turbulence parameter models, we used a turbulence modeling called variational multiscale methods. And we have used a Reynolds number of close to 4,000, which is like obtained from literature, whatever they have used. And these again are the other turbulent parameters, things like the time step that we have used and the Freudian number that we have used for the simulations. Again, this is just the qualitative comparison of results against the literature. We could see our simulations matched most of the profile that we are expected to see. Again, just to comparison, the one on the right-hand side is composed of 50 million meshes, and this is 0.3 million. Again, the objective is to make sure that it captures at least most of the fluid flow so that we can make some considerable study with it. Then once the implementation on GPU, everything is completed, then the objective was to scale ahead and do the full-fledged simulations. Okay, this is the velocity norm compared against the actual values mentioned in literature at different cross sections. Again, the one thing that you could see is the mesh that I have used is not wall refined. So you could see most of the differences comes at the region of the nearby region because I don't have a wall fitted meshes to perform this simulation. But as far as apart from that, it could see that it captures the high and low regions in the flow efficiently as much as the given low resolution mesh can handle. Again, with particle deposition modeling, it's the basic momentum balancing equation of the particle where the change in momentum is attributed to the force balance acting on the particles, which generally equates to drag force, gravity, and the Brownian. In our simulations, we didn't incorporate Brownian because all these Brownian force effects based on the literature they occur at a particle sizes which are less than 1 micron. So for this simulations, at least what I'm going to present here, the Brownian force has not been included. Okay, so for deposition algorithm, again, here we have not considered any form of bouncing of the particles. So the particles, when it impacts a wall with a certain velocity, we do consider the particle to be deposited. Again, the logics for structured will be the fact that it will find the new position of the particle outside the domain. Given that it moves with a certain velocity, we form a trajectory and we form the intersection point as the deposition point. However, for unstructured measures, the logics can be quite tricky because again, so when we can have a cell without any edges over there. So we imply other algorithms to make sure where it has deposited and all. So actually, this was the place where I found the actual having an actual FEM data structures found to be very helpful in CPU, because FEM, given to be the mesh rich data structure that it has, can calculate, we can identify like with cell, like the edge information, the normal information of that particular edge, and like it is easy to calculate those intersections and everything. However, when we started porting the code to GPU, we realized a lot of challenges. I think that we will cover in the next things. So these are the particle parameters that I used for modeling. We wanted to model an 8 micron particle to replicate the results from literature. Uh, for a glycerol particle at 20, the properties are taken at 25 degrees Celsius. Um, so the current logic is that it will check if the particle is outside the domain, then it will check if it's a boundary cell. If it is there, then it will compute the intersection. Then if the intersection is present, it will mark the intersection of that face. Else it will check if there is a boundary vertex which actually matches those intersection. Then if it checks actually if the boundary faces an the actual intersection face as an outlet face, then it will mark it as escaped, or else it will mark it as deposited. Okay, so we did some initial simulations. I don't think the browser handles the animations here, but we did the thing. So for a sequential implementation, just for 25,000 particles, it took around close to 500 seconds, which was not an optimal thing. So the first thing that we did was the making it a shared memory parallelizable. So the idea being the fact that we have to go through all the routines and make sure whatever the routines was not thread safe, to make them thread safe and make sure we were able to implement these procedures. And what did we observe was like, since the computations were very expensive, we observed a lot of particles that kind of either were stagnant. If you could look at the velocity at the top region of the flow, there is a low pressure region, so the particles will get thrown off over there. But due to inertia, they just like stay there for a longer period of time, where most of the particles exit the domain. And since my exit criteria was like at least 95 to 98% of particles should have either been deposited or escaped. So we have to write routines to make sure that if the particle is stagnant for a very long period of time, we kind of ignore it from the calculation. But at the end, we make sure that for how the percentage of particles that we have like ignored from these computations is well within their tolerance. Okay, so once it's done for the first implementation, we did achieve close to a 13x speed up for all particle sizes. This was done on system with 42 threads. Okay, it's an AMD threadripper system with 24 cores and like 48 physical threads should be available. And we were able to obtain a speed up of close to 13 for almost like close to all particle sizes. Okay. The one thing that we also realized is that here the idea behind parallelization was that each particle will be handled by one of the OpenMP threads. So here this particular number is restricted. However, in GPU, we could get a larger number of threads at our disposal. And if we could write effective algorithms, we should be able to get most out of the performance that is available in the GPU. Okay. Again, the main challenge that comes in doing these or doing the entire particle transfer within the GPU architecture is the lack of data structures. In sense, like In FEM in CPU, the data structures are mostly nested. So for example, you could take a collection of cells inside which you have a class for cell, inside which you have class for edges, and like it will be so and so. So one thing is like trying to decopy like this 10 level nested data structures to GPU might not be a good idea for two reasons. One, for the memory issues that, or the memory limitations that comes with the devices like this. And the second thing is the performance issues that comes with when you have data at these many nested levels of access. Trying to do this calculation in a single 3 threads might not give a good enough performance when you do these kinds of calculations. So again, the first idea is to get through the data structures that and try to get only the necessary data that needs to be taken from the CPU, transfer it to GPU, and then rewrite the FEM kernel routines, FEM routines in CUDA kernels that can use these limited data structures to efficiently interpolate the particles within the GPU. Okay. And one more thing is the current algorithm had like a sequential search of particles. So when a particle exits a particular cell, we have to search through the neighboring regions to find. But what happens was like um, again, this information of cell neighboring information is again very complex. If we can transfer it directly to GPU, obviously this calculation might be easy to be performed, but like realize that it was little bit more memory intensive, and also like it might impact performance trying to do all these access of taking a class, going to a value, and like keep going until you find a value from which the CUDA threads could do the calculation. So one idea was to get the zonal neighbors calculated in CPU and then transfer them to GPU. Take like for a single cell X, you can calculate a certain level of neighbors, store them in an array, and then transfer it so that you don't need those data structures there. But what we observed is that for certain number of cells in the domain at the level two meaning like, so level 0 is the immediate neighbors of the current tetrahedral cell that is being shared by all the DOFs in the current cell. So level 1 is the cells that are shared by the next level of cells, and level 2, it will keep on going in such a way. So we could see, at least to check 2 levels of neighbors, we could see the max cells that are being shared at level 2 were close to 1,300 cells on a 0.3 million element meshes. So which means that this brings one more problem. If you kind of interpolate that for a million cells, 1,000 data points, that itself will again take gigabits of memory to store the data, which might not be available in the GPUs that you perform these calculations on. So one thing that we understood as a simplified form is that mesh data, the raw mesh data structure in its raw form is nothing but a graph of connected vertices together, cells and DOFs connected together. So once we do an enough amount of pre-processing on the data, we should be able to get the adjacency matrix for all these cells and then store them in a CSV format, which can be like efficiently used to calculate the zonal neighbors that we wanted to like pre-compute in CPU. But however, using less memory, you should be able to calculate those details in GPU. So again, the idea was to use the CSR format data, pre-processed and saved in such a way so that when you import them to GPU, you can be able to calculate the neighbors of a given cell and all those data structures with minimal access and as like with minimal data as possible, so that the calculations are a little more effective. We did implement a breadth first search based search of neighbors for zonal until a given level, after which the particle is like not searched. Okay. So before we started comparing the performance of our model with the sequential one and provide the speedups, we wanted to make sure the sequential code that we have used is in fact the optimal, like is optimal to a best extent as far as our knowledge, so that the speedups when we portray have a good meaningful speed up rather than trying to compare it with a very non-optimist sequential version. So we did took the mesh, simple mesh on a ANSYS Fluent DPM with a 0.2 million size, and we tracked 100K particles. The total time taken was close to 0.6 seconds. And in our implementation, which is close to 0.3 millions, the time took 0.159 seconds. The reason why I didn't use the same mesh with ANSYS was because ANSYS has its own meshing module, and it does not allow me to export the mesh to a given format with which I can use it in our in-house FEM package that we have. So we try to be close as possible, but again, even with the considerations, the time was little better. And after which we moved on to the validation of our code with respect to OpenMP and the GP implementation. This OpenMP implementation was done with, again, 48 threads. So you can see for particles ranging from 100K to 5 million, the speed up of OpenMP was almost close to constant because of the number of threads is same. But however, you could see a good amount of increase in GPU speed up when the comparison is being done on GPU. But again, you could see the slope of that speed up is kind of slowly saturating. This is due to the fact that the even after certain range, the GPU threads will also be constrained. We cannot use more than certain number of threads, so the speedups won't be like keep on going up. But comparatively, when you compare it to a normal shared memory parallelization in a single system, this kind of provides a good speed. This approach of trying to do this inside a GPU provides us a good speed up. So now we did validate the results of our flow with the literature. So this is the left hand side is the deposition fraction achieved at different segments, where the green line is our simulation, the other two are the baseline ones. We could see it fits most of the profile except for certain region, obviously, which needs more meshing. And when it compares to the deposition fraction achieved at different particle sizes, again for higher size particles are from 5 to 10 microns, we are exactly matching the LES simulation mentioned in the literature. But after which, I think there is some discrepancy, which might be due to the fact that we have not incorporated Brownian force into this calculation. So we might need to, the runs are going on, we might need to check on that after this. I think this is just the visualization of the particle simulation. Let me try if I could play this thing. This was, I think, done for 1 million particles for 100K, 1 million particles at 8 micrometer diameter. We achieved a deposition fraction of 83.97%. Okay, so this is the thing. Again, the future slow scope for this would be to the idea of bringing the FEM data structures and everything into GPU comes with two advantages. One, it not only speeds up the existing algorithm, but there are projects that we did where it also acts as a substantial like secondary computing device, let's say for in ALE formulation, where I did the same thing and did the computations that were related to the mesh movement on GPU. Even though it is very slow, there was no speed up or everything when compared to the GPU. However, during my fluid solver is running, I could do the simultaneously that on GPU itself, which can like speed it up, which can like in overall give considerable amount of time savings. And doing this also can, like, we are also trying to look into studying more of particle dynamics in terms of, let's say, studying the FTLE computations. That also is very highly compute intensive, and like trying to doing that on GPU can fasten up the simulations and like can try to get more insights on the underlying physics. So again, this is an initial approach, try to validate this methodology of doing these calculations on GPU. You can, I primarily work on HPC and most recently on scientific machine learning related to physics-informed neural networks. So people who are interested can contact me. Thank you for being patient. I think
Okay.